This is the video for section 9.2 LOpps. Problem 5. You're supposed to find the sum of the first 5 terms. So if we just list them out, my first 5 terms are these. And we can add them together. Let's look at just how to show the sum of my first term is just itself 3. The sum of my first 2 terms is 3 plus 3 halves, which is 9 halves, which of course is 4.5. The sum of my first 3 terms would be 3 plus 3 halves, which is my partial sum of 2 terms, plus my third term, which is plus 3/4, which gives us 21/4, or 5.25. And I can continue the pattern till I get to the sum of 5 terms, which is exact sum is 93 over 16. And actually, this is exact as well. Dividing by that even number, we can eventually get to an end to our decimal. So we're supposed to determine if this series converges or diverges. We recognize it as a geometric series where the R is 3 halves, which is greater than 1. So by the geometric series test, this diverges. Okay. Number 9, again, we recognize it as a geometric series where R is 1.055, which is greater than 1. So this diverges by the geometric series test. This is what you have to write. Yes, you have to write all that information. Do not make shortcuts. Number 11, this one doesn't look quite as obvious to us. It certainly isn't geometric. So now let's see what happens when I look at the nth term. The limit as n goes to infinity of my nth term is 1, which is not 0. So this diverges by the nth term test for divergence. For problems 17 through 22, you're supposed to match your graphs to some series. Notice that this one's leveling off around 3, it looks like. This one also is doing that. Again, this is your first partial sum. This is the sum of the s when n is 0 and n is 1. This is the sum of when n is 0 plus 1 plus 2, and so forth. Okay, so this is your third partial sum, fourth partial sum, so forth. You can look at C. It also appears to be leveling out to 3. You can look at D. It looks like it's oscillating. It's not really oscillating, but it looks like it is converging towards a number. It looks like it might be 3. And if we look at E and we look at F, you can see what is happening. So what we're going to do is look at each of these series and try to find the one that it is similar to. So you might want to have your book open for this. So number 17, here is our series, and it's geometric with R being 1/4, which is less than 1, so we know it's going to converge, and we are told that all of these converge, but it's nice to be able to prove it. And so starting at 0, so when n is 0, I get 9/4, which gives us this sum. My sum of my first when n is 1, so my first and second term would be 9/4 is my s of 0, and then my term when n is 1 is 9/4 times 1/4. So we get 9/16 plus getting a common denominator. So s of 1 is 45 over 16, which is 2.8125. So s of 2 is going to be 45/16 plus, substitute 2 in up here at the top. So 9/4 times 1/4 squared is 1/16. We get that, which gives us 189 over 64, which is 2.953. You'll notice they seem to be getting closer and closer to 3. And so since we know that this is a geometric series, here is my first term, here is my ratio, so I can look at the sum is my first term over 1 minus my ratio, and we do in fact get 9 over 3, which is 3. And that is going to look like graph C. What's happening in graph C? Well, my first sum was 2.25. And if you look at graph C, my very first point is at 2.25. So if we look at graph C, here's our S of 0. S of 1 was 2.8125. There it is, sum of my first 2 terms. The sum of my first three terms was 2.953. There it is. And you can see that our sum is 3. So as we take it out to infinity, I'm leveling out to 3. What we can see here, again, we have a geometric series with r being 2/3, which is less than 1, so we know it converges. And since it converges, we can use our sum formula. Sum is my first term, when n is 0, is 1 over 1 minus 2/3, which is 1 over 1/3, which is 3. I can also list my first few terms. Okay, here's my first term, here's my second term, here's my third term. Notice my notation. A sub 0 is my first term. S of 1 means the sum of my first two terms, because S of 0 is 1. S of 1 is S of 0 plus this term. Okay. S of 2 would be S of 1 plus one more term. And I get 2.11111. We're going to level out using my sum of an infinite geometric series to be 3. And look at graph 3. It is. There's my first term. My second term, my sum of two terms, my sum of the first plus 2/3 gives me here to 5/3. My sum of the first three terms took me to 19/9, which was about 2.1, a little over 2. Notice that's a little over 2, and so forth. I'm going to go through the same process a little more quickly for each of the other problems. Again, geometric, absolute value of r is less than 1. I can find my first term. I'm starting at 0, so my first term is 15/4, and that is my S of 0. And then my S of 1 would be 15/4 plus what my next term is. My next term would be 15/4 times negative 1/4 to the 1, so negative 15/16, which gives me this, which gives me that. The sum, S of 2 is the sum of my first three terms, which is the sum of the first two plus that next term. And my next term, when n is 2, gives me this. We get that. Again, we could go through our geometric sum of an infinite geometric series, which gives me 3. And this is graph A. So let's look at my first partial sum is 15/4. That's almost 4. Right? 16/4 would be 4. My next sum would go down to 2.8. My next one's going to come up to 3.04 and so forth. You can see it's getting closer to 3, and it matches graph A. So looking at graph A, there is almost 4, less than 3, a little above 3, and it's going to get closer and closer to 3. Number 20, again, we know it converges. When n is 0, I get 17/3, and here is my sum. Again, I can list out my partial sums, S of 0, S of 1, S of 2. You can see that my first term is at 17/3, which is almost 6. Then I'm going to come all the way down to 0.6296, so a little over a half, right? And then back well above 1, and we're at 5 something. And so this matches graph D. So here we are. If we look at graph D, my first partial sum is almost to 6, and then it came down here a little bit over a half, and you can see it's doing this. As I add terms, my sum seems to be converging, and it is converging to 3. Number 21. Here is our series. Here is our series. Again, it is geometric with the absolute value of r less than 1. We know it converges. We can use our sum of a converging geometric series. It's 34/9, which is almost 4. 36/9 would be almost 4. So this is going to look like it's leveling out to around 4 as n goes to infinity. Again, I can list some partial sums just to kind of get an idea. 17/3 is a little less than 6. Then my next term is going to be my next sum. So my next plot on my graph would be close to 3, but below it. The next one is going to be at 4.25. Then we're going to be back a little bigger than 3. Okay, so we know that this is going to go close to 4 as we go, and that is where we are here. Notice there's my first term almost at 6. and then below 3, and then above 4, and then a little above 3, and so forth. And then our final series in this one, again, it's geometric with r less than 1. So my first term, when n is 0, is 1. My sum would be 5/3. Again, looking at my partial sums, by now you know how to get them. And so this looks like it's going to be leveling out a little less than 2. 6/3 would be 2, a little less than 2, and that is graph E. Leveling out a little less than 2. My first partial sum is 1. My second one was 1.4, a little less than 1.5, and so forth. Okay. So these problems give us an idea of what is going on when we're looking at series. So for the next problem, we want to verify that the series converges. So first thing I need to do is use my partial fractions and use the technique that we've learned from that. We know that we can find a to be 1 and b to be -1. So this would be written as the series as n goes from 1 to infinity of 1 over n minus 1 over n plus 1. And if we list out a few terms, when n is 1, I get 1 minus a half, plus when n is 2, I get 1/2 minus 1/3, plus when n is 3, and so forth. And I'm left with the 1/2s are going to drop out, the net 1/3s are going to drop out, and so forth. And I'm going to be left with 1 minus 1 over n plus 1. So my limit of my sum is 1. For the next several problems, we're going to be finding the sum of the converging series. So you're already told it converges, but it's good to know this is a geometric with r less than 1. My first term is 1, and my sum, using my formula, is 2. Number 41, again, we know this is a geometric series. My absolute value of r is less than 1. This converges. My first term of my series is 1. And again, using our sum of a converging geometric series formula allows us to find that the sum is 2/3. 43, 1 plus 0.1 plus 0.01 plus 0.001 plus, okay. You should be able to tell that your common ratio is 1/10. So we have a geometric series with r being less than 1 that converges. Again, using our sum formula gives us 10/9. 45. Here is our series. We want to recognize my first term is 3. It looks like I'm going to be multiplying by a negative. And from here to here, I'm multiplying by -1/3. From here to here, that gets me to that term. -1/3 gives me to that term. So there is my common ratio. The absolute value of r is the absolute value of -1/3, which is 1/3, which is less than 1. So this converges. And I can use, once again, that sum formula. Now, 47 is a very interesting problem. What we're going to do in 47 is make two different series. Okay, so we're just going to call this my a sub n, and this is b sub n. Okay, and so a sub n is geometric with my common ratio being 1/2. We know that's going to converge. B sub n is also geometric with my common ratio of 1/3. We know that's going to converge. And so I'm going to find each of the sums, and I have to take this sum minus this sum. Kind of a neat problem there. 53, the problem is 0.81 repeating, which means 0.81818181, and listing that out would give us 0.81 plus 0.0081 plus 0.000081 plus, and so forth. You can see that your common ratio is 0.01, which is 1/100th, which is less than 1, so we know this converges. And again, we can use our sum of an infinite geometric series. Now, we want to convert these to fractions because fractions are our friends. Froth. Okay? So this would be, my first term is 81/100ths over 1 minus 1/100th, which is 81 over 100 over 99 over 100. The hundreds cancel. You get 81 over 99, which can be reduced by a factor of 9. Gives me 9/11ths. 55, you have to be careful. 0.075, where it is the 75 that is repeating. So your first term is 0.075, which is 75 over 1,000. but the next term is 0.000 and then 75. And the next one would be 0.000075. Okay, and if you write these as fractions, you can see that I've got 3 zeros here. I'm adding 2 zeros, adding 2 more zeros, so my common ratio is 1 over 100. Again, this is a geometric series with my common ratio less than 1, so we know it converges. So again, we can use our sum formula. And just simplifying that, let's give it some thought here. This would give me 75 over 1,000 over 99 over 100. So dividing by 99 over 100 is times 100 over 99. These two zeros can cancel with those. So this gives me 75 over 10 times 99. So rather than multiply all this out, let's think about how we could reduce it. 75 is 25 times 3, so I'm going to write it as 5 times 5 times 3. That is because we can take one of the 5s and take it into the 10, leaving 2. We can take the 3 and take it into the 99, leaving 33. And so we get 5 over 2 times 33, or my sum is 5 over 66. 57. All right. Look at this series that n goes from 1 to infinity. We can see this is not geometric, so we can't be thinking geometric series. So since we only know one other test, why don't we see if it's maybe works with the nth term test for divergence? So we're going to look at the limit as n goes to infinity of this series, and we see that the nth term is 1/10, which is not 0. So this series diverges by the nth term test for divergence. All right, the series as n goes from 1 to infinity of 1 over n minus 1 over n plus 2. So what we see here is, again, it certainly is not geometric. What we can do is list out a few terms. You can see the 1/3 are going to drop out, the 1/4 are going to drop out, and if we continue, we will see that all we're left with is 1 plus a half, so that is 3/2. So this converges by the fact that it is a telescoping series. Number 61, the series as n goes from 1 to infinity of 3n minus 1 over 2n plus 1. Again, not geometric, so we're going to take the limit as n goes to infinity of the nth term, which is 3/2, which is not 0. So this diverges by the nth term test for divergence. 63, let's look what we can do to rearrange this a little bit. The 4 can come out in front. If we write this as 1 over 2 raised to the n, we can see that what we have is a geometric series with our r, which is 1/2, to be less than 1, so we know it's going to converge by the geometric series test. Number 65, n goes from 0 to infinity of 1.075 to the n. Again, it's geometric. This time our r is 1.075, which is greater than 1. So this is going to diverge by the geometric series test. And our last example, 67. Now what we're looking at here is as n goes from 2 to infinity of n over the natural log of n. Now what we need to know is, does n increase more rapidly than natural log of n does? Because we know natural log of n is always increasing, because its derivative would be 1 over n, always positive. So does n increase more rapidly than natural log of n, or does natural log of n increase more rapidly than n? That's going to affect how it turns out. Well, what we know is when n is greater than 2, n will be greater than the natural log of n. Think about it. When n is e to what power gives e? That's 1. Okay. When n is a number greater than 2, which e certainly is, let's let e be greater than ln e, and it is. Okay, e is 2.71828, ln e is 1. Okay, so when n is any number greater than 2, this is going to be greater than that, which means my numerator is going to increase more rapidly than my denominator. So the limit of n over natural log of n is not 0. So we are going to diverge by the nth term test for divergence. And there you have 9.2 LOpps.